Welcome, everyone. Today, we are exploring a crucial capability in enterprise machine learning operations, sharing assets across workspaces using registries. Let's learn how to break down data silos and scale our ML deployments safely. Let's start with the basics. What exactly are machine learning assets? When you build an AI solution, you are generating data tables, environment configurations, models, and reusable code scripts, which we call components. Typically, you store all of these inside a machine learning workspace. Think of a workspace as your secure, digital laboratory. We meticulously track these assets, often using tools like MLOps, because machine learning requires absolute reproducibility. If a data scientist trains a brilliant model, we must be able to recreate it. In the inner loop of development, assets are created and tested within this isolated local workspace boundary. Looking at this diagram, you can visualize the boundary of a single ML workspace. Inside this secure perimeter, we have all our critical artifacts, the data we train on, the compute environments, our MFlow-tracked models, and our pipeline components. Everything is neatly organized, but at this stage, it is confined to just this one specific workspace. Now, as your team grows, a single workspace becomes a major liability. If we train, test, and deploy in one place, experimental code might accidentally break a live application. To solve this, we adopt a multi-workspace MLOps architecture. We create entirely separate environments, a development workspace for pure experimentation, a staging workspace for rigorous testing, and a production workspace for live traffic. This physical separation is vital. It means your data scientists can experiment freely in dev without ever having access to the sensitive, real-world customer data that lives strictly in prod. This flow shows our enterprise setup. On the left, data scientists work safely in the development workspace. In the middle, our CI/CD pipelines run automated tests in the staging workspace. On the right, the production workspace handles live end-user traffic. The environments are perfectly isolated to guarantee security and operational stability. We've established our secure, isolated workspaces. But this introduces a massive challenge. How do we move assets between them? When a data scientist finishes training a model in the development workspace, that model is registered locally. The staging workspace cannot natively see it. If we don't have a seamless way to share these assets, engineers will resort to manually copying code or, worse, retraining the model from scratch in production. This breaks the fundamental rule of MLOps. We must promote the exact same artifact from the inner loop of development to the outer loop of deployment. We need a bridge. Look at the broken links in this diagram. We have our perfectly isolated workspaces dev, staging, and prod. But the local asset stuck in dev cannot cross the boundary into staging for testing. The isolation that provides our security has now become a bottleneck for our deployment speed. The solution to our silo problem is the Azure ML registry. Think of a registry as a centralized, organization-wide catalog that sits above all your individual workspaces. Instead of registering your newly trained model or reusable component to the local dev workspace, you publish it to the central registry. Instantly, that asset becomes securely accessible to your staging and production workspaces. This effectively bridges the gap between our development loops. By using a registry, we ensure that every environment is pulling from a single, authoritative source of truth, maintaining strict version control and perfect lineage across the entire enterprise. This diagram transforms our previous architecture. We now have the central ML registry sitting at the top. The dev workspace publishes its successful models and components up to the registry. From there, the staging and prod workspaces can seamlessly pull those exact, version-controlled assets down for testing and live deployment. Let's look at what we actually put into these registries, starting with components. Components are the secret to scaling ML development. When you move out of experimentation, you take your Python scripts like a data normalization step and package them with a YAML file that defines their inputs and environment. This creates a reusable component. By registering this component to the central registry, you unlock massive efficiency. Now, a data scientist in the staging workspace building an automated pipeline can simply call this exact component. There is no copying and pasting code. Everyone uses the exact same, centrally governed module. Here we see the anatomy of sharing a component. We take our raw Python script and our YAML interface and combine them in the component packaging step. We then register that package up to the central registry. Finally, that component is consumed directly by a pipeline job running in a completely different environment, like staging. Just like components, our models must be shared via the registry. During the training phase, we use mflow. By simply adding mflow.autolog to our scripts, the system records every metric, parameter, and model file. When we find the winning model, we don't just leave it in the dev workspace, we register it to the central registry. Because it's an mflow model, it carries all its environment dependencies with it. This enables an incredible feature called no-code deployment. When the staging workspace pulls the model from the registry to test it, it doesn't even need a custom scoring script. The platform generates the endpoint automatically. This sequence diagram outlines the model's journey. The dev workspace trains the model, and mflow captures the telemetry. The winning artifact is pushed to the central registry. Later, the staging workspace requests that specific model version. The registry delivers it, and staging instantly spins up a no-code deployment endpoint for testing. Registries make sharing possible, but automation makes it reliable. We orchestrate the movement of assets using GitHub Actions. We enforce feature-based development. No one pushes directly to the main branch. When a developer opens a pull request, GitHub Actions securely authenticates to Azure and triggers a pipeline. The pipeline trains the model, evaluates it, and automatically publishes it to the central registry. But automation still requires human oversight. Before the staging workspace deploys that new registry asset to the live production workspace, the workflow pauses. A lead engineer must grant gated approval, ensuring total safety. Here is our automated lifecycle. A GitHub pull request triggers GitHub Actions, which authenticates and runs a training job in the dev workspace. The resulting model is pushed to the central registry. It is immediately deployed to staging for testing. Finally, it hits our manual approval gate. Once the lead engineer clicks approve, the model is pulled into the prod workspace for live traffic. Let's tie this together with a real-world scenario. Prosware is a healthcare startup that built a diabetes classification model for doctors. Medical data drifts based on geography, so they must retrain their models frequently to maintain accuracy. Using our architecture, data scientists safely experiment on new data in the isolated development workspace. When they find a better algorithm, they merge the code. GitHub Actions automatically trains the model and publishes it to the central registry. The staging workspace pulls it down, runs tests, and after a lead doctor approves it, the production workspace seamlessly updates the real-time online endpoint. The web app never goes down, and practitioners instantly get the most accurate predictions. In our final diagram, we see the complete Prosware architecture. New regional data enters the dev workspace. The refined model is pushed to the central registry. It flows through staging tests, passes the approval gate, and updates the production workspace endpoint. The practitioner web app constantly communicates with this endpoint, delivering life-saving insights in real time.